We are going to look at calculating the pH of solutions. And if you know your titration curves and you know how to calculate the pH at the different places of a titration curve, then this will be really easy. So I'm going to give us 3 solutions. 2 will be just the thing by itself, and then we will mix them together. So the first one we are going to look at is 15 milliliters of a 0.35 molar solution of ammonia. Notice we only have ammonia, so we don't really care about the volume, we just care about the concentration. So the first thing I notice is that this is a weak base. So I'm going to need the Kb. So when I look up the value for the Kb, I can see it is equal to 1.76 times 10 to the negative 5. Now, I don't have anything else in solution, so I can calculate this as if I were calculating the initial pH of a weak base. So I know that the concentration of hydroxide is going to be equal to the square root of Kb times the initial concentration of our ammonia. Keep in mind, this is something that we've been doing all quarter. So when I plug my values in, I'm going to get the square root of 1.76 times 10 to the negative 5 and multiply that by 0.350. Now when I do that, I get 2.48 times 10 to the negative 3 molar. Now I can solve for the pOH, which is going to just take the negative log of that number there, and I get 2.61, and then I can subtract that from 14, and 0.39. So my pH is equal to 11.39. As you can see, this calculation is exactly the same way as calculating the initial pH in a titration curve. So the next one we're going to look at is 25 milliliters of a 0.125 molar hydrochloric acid. So here I know we have a strong acid. So there is no Ka because it is a strong acid. So I also know that for a strong acid, the concentration of my HCl is going to be equal to the concentration of my hydronium ion. And that is because I can take my 0.125 moles HCl per liter, and it's a 1-to-1 mole ratio when hydrochloric acid dissociates in water. And it is a complete dissociation, not a partial dissociation. So it does not exist in equilibrium. So I have 1 mole of hydronium ion per 1 mole HCl. So now my moles of HCl cancel, and I'm left with 0.125 moles of hydronium ion per liter. So that's how you can see that the concentration of your acid is the same as the concentration of your hydronium ion when you're dealing with a 1-to-1 mole ratio. So to get the pH, I'm just going to take the negative log of my 0.125, and that will give me 0.903. Now, in part C, we are going to calculate the pH of the resulting solution. When A and B are mixed together. So this is really like a titration curve problem because we have an amount of acid and an amount of base. And I notice this is a weak base and strong acid. So I need to calculate the amount of millimoles of each thing I have present. So we have 15 milliliters of base. So I can calculate the millimoles of base. And that gives me 5.25 millimoles of my base. Then I can do the same thing for my hydrochloric acid. I have 25 milliliters times 0.125, and that gives me 3.125 millimoles of HCl. So I can set up my neutralization reaction. And again, remember, chloride is a spectator ion. We don't care about it. It's not participating in the chemistry. So I'm going to start off with 5.25 millimoles here, 3.125 millimoles here. I don't have any of my conjugate acid yet. So my acid is going to be completely consumed. And I can see how much I have of each thing. So if you're looking at this, I have more base in solution than acid. So that lets me know that I'm before the equivalence point. So if we're before the equivalence point, remember, we can calculate the concentration of our hydroxide using the equation Kb times ammonia divided by ammonium. So when I plug my values in, we get 1.76 times 10 to the negative 5 times 2.125 divided by 3.125. Remember, I can use millimoles here because I have millimoles on the top and the bottom. If that wasn't the case, then I would have to divide by the total volume. So this gives me 1.1968 times 10 to the negative 5. Now I can negative log that to get a pH of 4.92. And then I can subtract from 14 to get a pH of 9.08. So you can see that when you are combining two solutions, you approach it in the same way that you do a titration problem. Calculate the millimoles of each, figure out where you are on a titration curve.